in Ahmed talks, you will hear about the resolution or the reason why the previous argument by Hawking, we think it's not correct, and we now think that indeed that central dogma is probably correct. Okay, thank you.
Thank you, Juan, for that very nice introduction. I knew very little about black holes until a few years back, and it's through listening to people like Juan that I've ventured to talk about them a little bit today. So my own interests are not so much in black holes per se, but in a central ingredient of the theory of black holes that Juan was presenting, which is quantum entanglement. So I'll introduce the basic ideas of quantum entanglement and discuss how they apply not only to black holes, but to many other things in laboratories around the world. So from Juan, we learned that black holes have an entropy and a temperature, and the entropy, meaning the number of degrees of freedom, is proportional to the surface area. To complete the list of things that you need to know, there's one other thing that I'll add, and that black holes have a amazing ability to just very quickly become black. So if you throw a star into it, it'll very quickly become a slightly bigger black hole, which is a perfect sphere. And the time it takes to that, you can relate to the time it takes for the black hole to reach thermal equilibrium, because the perfect spherical shape is in thermal equilibrium. And it turns out there is a fundamental speed limit on how fast things can equilibrate. And the black holes seem to be exactly at it. So then a question becomes, if you want to now make a quantum computer that's going to simulate a black hole, meaning, if you got a bunch of qubits, these are ones and zeros, which are behaving quantum mechanically, and you couple them together, the theory tells us if you couple them just right to an outside observer, that these qubits will look like a black hole. So we can ask, well, what kind of quantum computer do we need? What are some of the features of this computer? Well, Juan already told you that the number of qubits, the number of ones and zeros you're going to need is very, very large, but it's proportional to the surface area of the black hole. And to have the other feature that they relax to thermal equilibrium so quickly, you need long-range entanglement. You need something that's extremely strongly entangled. So what is quantum entanglement? Well, the idea of quantum entanglement, well, later on, I guess, often referred to spooky action at a distance. And this spooky action phrase has often been ascribed to Einstein. And I thought that was a fake story until Ahmed went to the Institute library and found that he actually used this word in a letter to Max Born. Okay, there it's in German. I won't try to pronounce that, but Einstein said, I cannot seriously believe in quantum entanglement because the theory cannot be reconciled I can't read it, with the idea that physics should represent a reality in space and time, free from spooky action and a distance. So what he's referring to here is a strange feature of quantum mechanics that when two particles or two qubits are entangled, if you perturb one or look at one, it immediately affects in a spooky manner the other one. Now, the idea of spooky action actually is very old. It was accidentally discovered, but not in this language, by Auguste Kekule, who was a chemist in the 19th century thinking about the benzene molecule. And I found in Wikipedia this quote. What happened? So Kekule spoke of the creation of his theory. He said that he discovered the ring shape of the benzene molecule after having a daydream of a snake sneezing on its own tail. So what was this picture of benzene molecule? So benzene has 6 carbon atoms, and just focus on a single electron on a carbon atom. Now these electrons like to form covalent bonds represented by this ellipse. So here in this covalent bond, you have one electron which is spinning one way and the other the opposite way, or vice versa. And this, of course, Kekule didn't know, but he knew that the electrons like to form this bond. But if you have 6 of them in a ring, there's no symmetrical way for them to form this bond. You can either choose this one, or that one. You can either choose this one or the other one. And the answer, Kekule said, well, it's resonating between the two. Somehow he had this picture that these two distinct physical states are both present at the same time, and the molecule is oscillating between the two. Well, in quantum mechanics, we say that it's really entangled. These are 6 electrons that are entangled, and they're in both of these states at the same time. So that's the very simplest example of entanglement, which occurs in something as simple as the benzene molecule. Okay, but we now want to talk about not just 2 of these, not just 6 electrons, but really a very, very large number of them. So I can say I had this idea, my spooky dream, based on the Indian game of snakes and ladders, where you just imagine that the snake is entanglement, and it can go from anywhere to anywhere. Anyway, okay. So then I've introduced a very simple model, now called the SYK model, which teaches us a lot about what happens when you have many electrons all entangled with each other. So imagine there's a set of random positions on which electrons can reside, and you put a few of them in some of the positions. And now these electrons are going to move around, and you want them to move in a way that they entangle with each other very strongly. So for example, you can imagine this pair of electrons moving from here to there. And this will happen in the quantum theory by at some rate. And that rate is characterized by a complex number, which describes the quantum evolution of the many particle state. So there's lots of possible motions here, each with, where you take a pair of particles moving from those 2 sides to those 2 sides and so on. And this, it turns out, an interesting model, but it's extremely hard to solve. But what we realize that you can solve this model if you just assume that each of those processes has a random number associated with it. So this is one of those instances that happens occasionally in physics and computer science too. When you make a problem random, it somehow becomes easier to solve. So we could solve this problem and then really understand in a simple case what happens when you have many, many particles entangled with each other. Okay. All right. So it turns out that this type of model has entanglement at all scale. It has a scale invariant structure, and the dynamics is sort of universal. And it turns out to then describe not only electrons moving in a metal, what's called a strange metal. It appears in the compound called yttrium barium copper oxide. But if you take a different view of it in a dual set of variables, it describes certain types of black holes. So there's this amazing connection between motion of electrons with lots of entanglement in a little crystal in the lab to what's happening with quantum entanglement on the surface of a black hole or inside a black hole. So here's an example of this material I just mentioned, yttrium barium copper oxide. It looks like that. And if you dip it in a bit of liquid nitrogen and set it over magnets, well, it's a superconductor, and it's an ability to just float and carry current without dissipating any energy. Of course, at that point, it's heated up. If it hadn't heated up, it'd keep going forever. So these are very useful materials put to many uses. Probably the most exciting is this company called Commonwealth Fusion Systems in Massachusetts, which thinks it can use these new materials to make clean fusion energy. But all right, so this is just their own promotional blurb. I'm not a recommendation to invest in this company. All right, so I've told you a little bit about this strange metal, this strange material, like by BCO, which has entanglement at all scales. Why does it describe a black hole? So here I'll just say a few things about that and conclude. So here I want to focus on a particular type of black hole, which there's a net charge. And for these black holes have the feature that if you're falling into them, if you were unlucky enough to fall into this black hole, it would feel to you as if the universe has become one-dimensional. There will be only one space dimension, and the transverse directions would disappear, would decouple, as we say. So in the end, when you're unlucky to be falling into a black hole, but you're lucky because you're living in a much simpler universe. You're living in a universe, there's only one space dimension. And then we can apply some of the dogmas that Juan discovered to this much simpler universe with only one space dimension. And one of the things that Juan told us, that if you want to make a quantum computer, that quantum computer should be in one lower dimension. So in this case, you're in one space dimension, so your quantum computer should be in 0 space dimensions. So do we know a quantum computer in 0 space dimensions? Well, that's exactly the SYK model. And so there turns out to be a rather explicit connection between the dynamics of these entangled electrons and the dynamics in this very peculiar type of black hole, which probably doesn't exist out there. But it's a very useful playground to test these theories.